So what we're looking at, we've got this function here, and we want to know where it may have vertical asymptotes. So vertical asymptotes arise from places where the function is undefined and it behaves in a particular manner around that point. So before we can even answer that question, we need to answer the question, what's the domain of this function? So let's take a look at that. So what is the domain of f? So what operations am I doing that could get me into trouble? Well, I'm doing the square root operation. I'm doing division. And I've also got a secant function. And remember, the secant function we can think of as 1 over the cosine of x. And so really, the secant function is just another division problem. It's going to be undefined everywhere the secant is undefined, but that's going to be everywhere the cosine of x is 0. Comes out to be 0. And so for the square root, for this part, we need x to be strictly greater than or equal to 0 for just the square root part. Okay. But notice for the division, we cannot have, so x, the square root of x cannot equal 0, and the secant of x cannot equal 0. And then for the secant is undefined wherever the cosine of x is 0. And so that's all the multiples of what? Well, those are all the multiples of pi over 2. So ... minus 3 pi over 2. And I should be a little more careful. All the odd multiples of pi over 2. So minus pi over 2, pi over 2, 3 pi over 2, ... So this is where the secant's undefined. Division would be when this comes out to be 0, so that actually tells me that x can't equal 0. And the secant is actually never 0. So that's not a problem, in fact. And why is that? Do you remember what the secant curve looks like? If we look at its graph, it has these asymptotes at pi over 2, all the odd multiples of pi over 2, which we sort of just alluded to. But it has this sort of horseshoe shape to it as it runs through those periods. And so it never equals 0. The y value never outputs a 0 there. So that's no problem. And so I think I'm ready to say that the domain of this function is all the numbers between 0 and pi over 2, unioned with pi over 2 to 3 pi over 2, unioned with 3 pi over 2 to 5 pi over 2, and then it continues on. So now that we've got the domain, we're going to have asymptotes wherever, so let's just say, now that we've got the domain, we know that each one of the exclusions in the domain, 0, pi over 2, 3 pi over 2, 5 pi over 2, those are either going to give rise to a vertical asymptote or a hole. Okay? And so if A is excluded from the domain, so if A is excluded from the domain and the limit as x approaches A of f of x equals a number, that shows that there's a hole. And if the limit as x approaches A of f of x equals infinity or minus infinity, or any of the left or right hand limits equals infinity or minus infinity, then we've shown that there's a vertical asymptote. Okay? So at this point, we're going to take all of those exclusions in the domain and we're going to look at the limit as x approaches each one of them. Okay? Well, that's quite a few to check, but it turns out some of them will fit under one category. So let's do the first one. Let's look at the limit as x approaches the first exclusion in the domain, which is 0. Ooh, here I have to be a little bit careful, because my domain didn't start until 0, so the only way I can approach 0 is to approach it from the right. And if we look at that, that'd be 1 over the square root of x times the secant of x. And this is section 2.4, so we do have a way of talking about this. What I'd like to do, just to make our lives a little bit easier, let's go ahead and rewrite this as the cosine of x all over the square root of x. Is that right? So this is secant is the same thing as 1 over the cosine, so I could multiply the numerator and the denominator. Yep, that looks good. And so this limit, the numerator is approaching, well, so this limit, let's just go ahead and say what it is. This limit is infinity. But let's see why that is. The numerator is approaching the number 1 up top, all divided by, and then the denominator is approaching a small, but what? Positive number. Why is it a small positive? Because we're approaching 0, and that's always going to be positive as we do so. And so we've got 1 over a small positive number, and that's why that limit is infinity. So we just showed at x equals 0, f has a vertical asymptote. Let me pause there. Oh, it's still running. Come on. So folks, here I've got the graph of this function, and you can't see my... So folks, here we've got the graph of this function, and you can see, sure enough, this graph has a vertical asymptote at x equals, hopefully you can see my mouse, as x approaches 0 from the right, it becomes infinitely large, so that gives us that vertical asymptote. We see here is pi over 2, here is 3 pi over 2, and here is 5 pi over 2, and we don't have asymptotes there, but if we were to click right on that pi over 2, this graph actually incorrectly says that the answer is 0. So the graph is actually making a mistake there. It's actually undefined at pi over 2. Okay. But sure enough, we've got a hole there. Okay. So even though so in this case, Desmos is actually sort of lying to us. It thinks that it's there's a value defined there. It's not. It's that there's a hole there. There's a hole at the ordered pair pi over 2 comma 0. That's what we just confirmed, and that would also be the case for 3 pi over 2, which is right here. There's that 0 right there. It's actually not a 0. There's a hole there, but Desmos is sort of lying to us. It's not perfect. And you can check that to be sure. If you took 3 pi over 2 and plugged it into this function, the secant of 3 pi over 2 is undefined because you've got an asymptote there on its graph. So anyway, I hope that helps, folks, and we'll take a look at more questions.